I derived the magnetic field due to a loop, and I got that expression right there on the z direction if you're on the axis of the loop. I want to do a different derivation that looks a little bit easier, but I don't like. Mine was kind of complicated, right? We did the cross product, we did all this stuff. If you can't find that link, it's part of my playlist down below, but if not, just put a comment and I'll show you where it's at, because, I liked it. But if you're in Griffiths 5th edition, or is it the 4th edition, Griffiths derives the magnetic field due to a loop with a different way and does a trick. I want to do that trick way so that you can see what's going on. Okay. So here I have a loop. It's coming in and out of the board right there. So the current's coming out this way, and it's going into the board that way. So the first thing that we have to do is say, well, look, I don't know how to find the magnetic field due to a loop, but I know the law of biot-savart. Biot-savart says the magnetic field due to a moving charge, mu naught over 4 pi q v cross r hat over r squared. I'm trying to decide right now if I want to do r hat. No, I want to do r. Let's do r over r cubed. Okay. And then if I have a wire, I can break that wire into a bunch of tiny little pieces and replace qv with idl. So I get dB, the magnetic field just due to one of those little pieces, is mu naught over 4 pi I dl cross r over r cubed. So what I need to do is to find the magnetic field due to all those pieces and add them all up. And that's what I did before. But now let's do it with some tricks. I'm not a huge fan of tricks. Tricks are for kids, but I just want to show you how they did that. Okay. So what we're going to do is to find the magnetic field at this location. I want this distance r. That's my vector r, but let's just call it r. So that's r. This is z in orange, and then that's r. So I have a right triangle. Now here's the first trick. If I just look at this top piece up here, and then I can call this the angle theta. If I call this the top piece, I'm looking at just that top piece, I want to find the magnetic field. So here I have the magnetic field, the current's coming out this way, I dl. R is this way. So R, I dl cross r is going to be a vector. I'm looking for it. Let's use purple. No, I use that pink. So not only is that the direction, but it also has to be perpendicular to r, right? When I take the cross product between two vectors returns a vector that's perpendicular to both dl, which that is, and r, which it is. Okay. Now, what if I do the same thing? Every part of that ring, the circular ring, has a corresponding piece down here. So I actually have another r, and I'm going to get another dB vector. And they're the same distance at the same angle. Everything's the same, except that they're in different directions up here. So really what's going to happen is the component in this direction is going to cancel. So we only need the z component. That's the first trick. We can just kind of plausibly say all we care about is the z direction. Okay. So we need to find the z component of that vector. I didn't want to mess it up down here too much. So this is the angle theta. I want to find this angle right here is also theta. So how can we do that? Well, look right here. This is theta. So if I draw a line like that, then this is the angle theta. And so now I have a right triangle. So that's theta. So this is theta sub c, the complement. Now I have another right triangle. So that's the complement of theta. That's the complement of the complement, which is theta. So the end of the thing is to say dB is going to be equal to mu naught over 4 pi. dl is perpendicular to r, so that's the cross product, just dl times r. So I get I dl r. But now I have to include this component right here. So I want the cosine of that function, of that vector, cosine theta over r cubed. So, and that's dBz technically. And you'll notice right here, that cancels with that, and I get r squared. Okay, so I still need an expression for r. I need an expression for theta, and then I can integrate. You know I don't have to integrate though. Okay. So let's find r. R is going to be equal to this distance, but it's a right triangle. I know that's capital R and that's z. So this is the square root of r squared plus z squared. What about cosine theta? Well, cosine theta is equal to adjacent over hypotenuse. So the adjacent is going to be r, and the hypotenuse is r, which is the square root of r squared plus z squared. So let's put that in there and see what we get. And in fact, I'm not going to replace the cosine theta first. Let's just replace the r. So I have dB z is mu naught I over 4 pi cosine theta over r squared, which is this, squared, so r squared plus z squared. And then I have dl, right, that dl. So now when I integrate around the whole path, I can integrate both sides. Well, the only thing that's going to change as I integrate is dl. Everything in here is constant. They all have the same angle with respect to that thing. So I get bz is mu naught I over 4 pi cosine theta over r squared plus z squared. And then dl, the integral of dl around the whole path, is just the length of a circle, 2 pi r. So this cancels, that cancels, and I get bz is equal to mu naught I over 2 r cosine theta over r squared plus z squared. Okay, so this is different than that because it's got the cosine, but it's still useful, and they actually use this in one of the problems, and that's why I wanted to derive that. But now what if we get rid of the cosine theta? What if I take cosine theta and put it in right here? I get mu naught I over 2. Cosine theta is r, so I get r squared, and then I get the square root of r squared plus z squared times r squared plus z squared, so I get r squared plus z squared to the 3/2, and I gotta box it. That is equal to that. Same thing. Now, which way is better? You know this way is better, right? Because we didn't make any assumptions about the directions and stuff like that. We did all that manually. So if you want to go see that video, and like I said before, playlist down below. That's that. Talk to you later.